you guys can see my screen. So like I just wanted to kind of draw out what is happening with concurrency. Um, and so Nick, you asked like a good question, like where do we use concurrency? Um, and ultimately, like the question is like, can we divide this program? I think there's two questions, and Kyle, feel free to add on to it, of course. Um, One, can this program be divided up? Can the execution of this program be divided up? And and two, are we looking for speed? So
I would add so speed, yeah, that's kind of goes hand in hand with
yes,
the first thing of like, can we divide this task up? One of the main uses of parallelism is, does your a good question that you need to ask is like, does your question or does your application need to do more than one thing at the same time?
right.
Right? So something like a background task, like say you've got a chat application that needs to um, and like, and this really is more relevant in like uh, high throughput scenarios, like where you have a lot of people interacting with it. Um, like, do you need to upload a file to the database while you're still serving chat requests, right?
Hmm.
Because if it's a single threaded application and you've got a file upload going on your main thread, like each thread of your application can only do one thing at a time, right? So you can think about it like each thread is like a timeline in which execution can occur on. Um, and so if you need to do more than one thing, you need to use asynchronous programming.
Yeah.
Um,
Yeah.
and so
And
we'll get into that a little bit. Yeah, Galen was saying you can divide up, like say you have like a really big job, um, and depending on the number of cores on your CPU, you can divide that job up to multiple cores on your CPU. That's another thing that you can do. But one of the most things that this comes into play with is like web servers and real-time systems.
mhm. Yeah. So like for example, I think web serving is or web servers are kind of like the sneaky best example here, because we're all familiar with them. We're literally on a web server right now through Jitsi. Is that we have like our master program, which like kind of like in the case of a web server is going to like is going to read from like socket inputs, so like incoming requests that are going to happen. um it's always going to be like checking for that. There's going to be one core program, and like in Obelisk we're using Snap, and so like a lot of the HTTP libraries and Haskell kind of like make this very easy for us, or like we don't even realize we're doing this. We're just kind of like saying like run snap, and it's handling all this for us. Um, but like for each individual like reads read of that socket that happens, it's going to be creating another process. And so like if I you know make a request um, to Ace, let's say. So I can't type here. Then I'm going to have an individual thread, or and like individual program, so to speak, that is running for myself, and then this is going to continue to read sockets and check for incoming requests. And so, if Kyle makes a request, then um, it's just going to simply fork another process, fork another thread, and that is going to be continue to run on its own. And assuming we haven't done anything crazy and chaotic, like assuming that these are just like read from the database requests, these have nothing to do with each other, right? My request has nothing to do with Kyle's. Um, from a security from a security perspective, we also would never want them to interact with each other. Um, there's just again no good reason for it, no need for that information to be shared, and that's ultimately what we're doing. And this kind of like goes into this can of course go into the millions. You can have like we could in theory fork however many like millionth thread, right? And each of these threads is going to show up or is going to show up as a process on our computer. Um, so actually, I'll bring up. I wasn't planning on doing this, but like if you're on Linux, you can just simply type in htop, and you'll see what all the threads that are running on your computer, all the process and threads that are running on your computer. And as you can see, I have like a absolute ton. Some have been running, like this one's been running for TeamViewer has been running for 4 hours. I don't know what it's doing, but it's not even using any CPU or memory. And we can see what's actually currently in use, right? So all of these are using some amount of my CPUs. I have 16 cores on here. This is like a heavily upgraded computer, I guess. Um, and we can see how each of these individual threads are taking up actual key resources on the computer. Right, and so I just wanted to make the difference between that the abstraction is, or like, between those two things, is we can have a million threads even if we don't have a million processors. And even I'll mention too. This is kind of like not the focus of what we'll be talking about today, but like with GPUs and with machine learning, um, the task of machine learning can be divided up and sort of parallelized. So that's why we can use GPUs, is because each individual GPU, which is responsible for a region of rendering this part of the screen, right? Like let's say like this section of the screen is one GPU that runs in parallel to all of the GPUs which work alongside it. And so that even is yet another example of parallel processing, which I think is interesting because, like, I think intuitively, I would guess that like the task of rendering a full screen would become or would be a sequential process, or like would be something that you can't divide up. Um, but like when you think about it, the question is like, does this block influence or does this block act as like an input, or like is this important information about what's happening in this block for this next block, right? And so like if that was the case, that I need to know what's happening here in order to know what's happening here, then I can't parallelize my GPU, which is obviously not true. But like, yes, we can because um, you know because of the way that like frames are chosen. I mean, when you think of like a frame, it's really just like a list of lists in a way, um, of RGB values, and um, a list is a data type that is very easy for us to parallelize. And right, we can even just think about it like, there's a way that you can build this frame, and then this section of the frame, assuming the frame is just a data type, right? It's just a piece of data. Um, then there's no reason that data one relies on data two. And that goes for any list, right? Like if we have um, sort of any list here, that's fair. Um, you don't know what ncREPL is, and that's because it's a short form on my computer for just Nix shell install the particular packages I need, and then go into Cabal REPL. I guess I did a lot of stuff. Okay. Um, but I just wanted to show, you know what, I can even show it even easier here. Oh, wrong way. Right, like I'll even go back to this master program example. If we have like a list of like request one, request two, and request three, and these are kind of procured data types that we have like generated from this master program, right? We've read the sockets, we've taken the bytes, we have some function here, um, read socket into rec, and this is going to take a byte string, right, which is just like the information contained in the file, and it is going to give us back a request. So, you know, um, and that's just how this has nothing to do with concurrency or parallelism here. We're just saying how to read a socket into a request. But once we've done that action, however we've done that, however we've made that implementation, and we have a list of requests, something like this can absolutely be parallelized. And it's like I guess the overall point I'm trying to make here is that I've never seen a case where you have a list of data types that are like built and no longer depend on each other, um, that can't be parallelized. So like for example, if we wanted to like a really simple example here is like let's say we had just a list from 1 to 10, right? So this is shorthand in Haskell for 1 to 10, right? So this will evaluate to being literally just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I don't have to write it all out. I could take this and then I could say map m print, um, let's call this x's, or I guess well, that's one thing I could do. This would be sequential though. So let's say par map m, which is a function I've made up, which is going to do two things. Um, and this is going to like fork another program and then print it, which is actually this is quite easy to define in Haskell. I'll forego it for now, but it's actually quite simple. Probably would have been simpler than even calling it par map m. But this is one example of like a very simple parallel program I could create. So, each individual element in the list has nothing to do with the other elements, so I can parallelize that. And so like the point I'm trying to make there is that like you'll start to notice um, like the patterns in data structures that we have in Haskell, um, and how they map to something that can be parallelized. So, but just as a counter example now, is like, let's say we have a, a function. Oh, that's interesting. I didn't know that would happen. Um, let's say we have a function. We want to find the sum of the x's. Then this is not something that can be easily parallelized. We could, in theory, parallelize anything, um, but there's a reason we don't want to. And the reason we don't want to here at a high level is because each element depends on each other, right? We're conjoining these into sort of one value, and so it's hard to split up the values and have each thread go on their merry way with the information that they need.
I will say, sorry to barge in, but say you wanted to sum like a billion numbers, you could use multi-threading for that
Yes, and so
because it depends on the I forget what they call it, associativity or whatever of the basically like it doesn't matter what order you sum up these numbers in, they'll always come together. So what you would do is you'd split it up into
yes,
say, 100 or 1,000 arrays of a million numbers. You'd sum those all up, and then you would sum up the 1,000 arrays. So it depends on the operation that you're trying to do, whether you can easily parallelize it or not. But I do think that like summing, for example, summing an array, you could do.
Yes. Yeah. So you could. You absolutely could. The question is just like what's the trade off here? So um, and then I guess you do, you know, yeah. So uh, in the case of like 10 values, it doesn't make sense. In the case of over 1 million values, it might make sense. And the reason for it is that what is the overhead? The question is what is the overhead of forking a new thread? Does it is it quicker to just simply do everything sequentially, or are you going to gain speed by forking a new thread? So let's say this is a contrived example here, or not a real example, but let's say it takes 3 seconds to fork a thread. You wouldn't want to do that for this because you could in a second say what's the sum of 1 to 10, right? And you get 55. That's very simple. But if we did say what is the sum of, it's going to start to take some time,
Yeah.
right? And so already we can see this is taking more than 3 seconds. And so the question is the evaluation strategy that we have here the fastest? Right? And so if we just assume again that it takes 3 seconds, right? Not true. It's quicker than that, but it's 3 seconds to fork a new thread. Um, we can see that this is taking more than 3 seconds, and so we can do the math about how easy it would be for each individual segment to run on its own, get forked, and then conjoin back together, right? Find the sum of each result, um, and we can evaluate which one is quicker. And so Kyle makes an amazing point that it also does come down to um, yeah, the points I mentioned about can this data structure be parallelized, but is there just enough data for us to work with to care about a parallel program here? Um, and so even too I mean a server, we kind of take for granted that a lot of libraries out there are they've existed forever. They know what problems you're going to deal with for scaling, and in theory you could have a you know well, no, not really, not easily. In theory, you could try and write a web server that's sequential, that is not parallel. Um, but you would deal with an issue where you quickly deal with an issue where you just have too many incoming socket requests, and it just it would not scale well. And so I don't know, I think a lot of the times it ultimately does just come down to performance. And even to the same with you know machine learning, if the training set is not enough, it's a very small amount, it doesn't even make sense to parallelize or run on the GPU in some cases. Um, Sorry, I just also realized that my charger is in the other room. I'll be right back. 1 second before my computer dies.
Hey, Carl.
Hey, how's it going?
Yes, I'm great. So, I just want a wish to ask, while considering the architecture of, of designing maybe an implementation of implementing maybe a data structure, the choice of whether to parallelize, I think, is it dependent on what we foresee in terms of computation in the long run, or is just based on a minor decision on.
Yeah, yeah.
like an intern.
It depends on your goals. So obviously, like when you're first writing a code, maybe for yourself or like for like your own personal project, some of these performance considerations aren't like you're not going to immediately see the benefit unless you're creating performance tests. But so one of the tricky you bring up a good point because one of the tricky parts about writing performant code when you're just doing it yourself is that there's only one of you, right? You, like you, typically, like we're used to running our applications and just interacting with it either through a terminal or in a web application. Um, but the reality is, once you get into like a job where the company has maybe thousands of people that are interacting with their application, that's when you really start to notice these things. Like if without thinking about these things, you can actually get into situations where your users are receiving timeout errors because they're just like say there's like in the worst case possible, if you had 1,000 people trying to read from a single threaded application, then basically it would work like a queue. Like whoever gets there first gets the response back, right? And so if you've got a long enough queue of people waiting to get a response, um, then it's some people are going to time out, some people are going to like they're not going to get their answer. A lot of times the answer will be stale if it's a real-time application, like they'll get something from like 20 seconds ago as opposed to right now. Um, so it's really a problem that shows up as more people start using the application. There's certain types of strategies where like you'll notice it right away. Um, the best example of this is like on a front end web application. Um, if you try to now, a lot of the web frameworks nowadays kind of simulate this concept, but like if you were to use like maybe we could probably show this sometime in the future. Um, if you were to use like JavaScript, just vanilla JavaScript, just regular plain old JavaScript, and you were to be doing some like heavy processing on the main thread, then you wouldn't be able to click a button, right? That's like a simple example of
Yeah.
like where threading comes in. Like I think a lot of people you use threads every day, just without knowing, right? Um, like this call right now, the fact that the timer is ticking up at the top, I'm able to say hello, and there's a video stream coming in. These are all happening on different threads on the computer, right? Um, and so it's the idea that like in an application, you want to be able to compute multiple things at the same time.
Mhm.
Um,
Okay.
so
And I
yeah,
also know, and
yeah, go ahead.
also thank you very much on that. Thank you very much. I mean, also know, Gavin was driving towards this. I don't know if now what is or what do we base on choosing whether maybe a particular task needs to be threaded? I mean, because definitely there are some tasks that will be more cost benefit to make it
Yes.
linear rather than threading. So,
Yep.
I mean, what are some of the factors that we consider in terms of choosing what tax should be threaded or
Yep.
not?
So some of them will be obvious because it just won't work. Like there'll be so there's kind of two ways that you can either do it for performance benefit, which is I think what you're talking about. But there are also cases where like you simply need to have multiple threads. Otherwise, like what you're trying to do just won't work. It'll be like because you'll get into a situation called thread lock where when one thread is doing a lot of processing, it locks itself, so it can't do anything else. Um, so you might experience thread lock. That's pretty obvious. You can test that out like while you're running your code. You'll notice, oh, this isn't working. Um,
An
but
example of that too would be like if it can't read in new requests because it's just dealing with too many requests to begin with. If it just like
yeah,
fully rejects the request.
if you had let's say you had a single threaded application and you're reading in a request from a socket, and then that request is like going through like 10 million lines in a database. It's grabbing a bunch of values, and then it's like doing a calculation on those values, right? That takes a lot of time. So if anyone else tries to hit the application in that amount of time, or in the same time, they won't be able to. The thread will be locked. The socket just won't even read. They'll just get an error. The socket won't be able. It won't be the socket won't be in a reading state. So that's the one example. The second one is I think for performance, which is I think more along what you're like asking about. It really comes down to compute cycles. So like the actual number of cycles that our computer uses. To fully understand this, it kind of gets into um, like how a CPU works. But at a high level, like each instruction that so we work with like high level languages, right? Has anyone here worked with like C or even assembly?
Yeah, I've worked with C before.
You've done C? Okay. So you know that C is like a lower level than like
Python.
JavaScript or Python or whatever, right? Yeah. And so it's closer to the hardware. So C is actually just one step above assembly. And so what C compiles down to are a bunch of assembly instructions. Galen, can I share my screen for a second? Because
Yeah.
I want to kind of show this. I think this is useful.
I think you
Um,
can also just share your screen
oh,
too. Like
can
you
I?
don't have to stop. Yeah.
Okay. So just to give, because I think hopefully this answers your question. Give me a second here.
And also too, I mean, the actual concept, like the Haskell piece, is going to be very simple to go through. So I think
Okay.
the core, if we do a good job of explaining like the domain, then
I can see myself. Okay.
hi
So
Kyle.
if you look on, there should be two screens being shared now. If you go over to my screen, then you should see.
I'll stop sharing my screen for a second just to like.
Okay. So I'm trying to find a good example of, and again, all of this is just on the fly, right? So we're not prepared for this question. Give me a second to try to find something. Okay. So basically, your code will get compiled down. So even in Haskell, because Haskell compiles to C and then C gets interpreted by it as an assembly language. I think was
Fun,
it ML?
yeah. Fun fact: it gets compiled down to C minus minus.
Yes, C minus minus, not C plus plus. I don't know why they did that, but it's funny. Um, it's like a special version of C that they created, or that was created for like functional. Anyways, it's basically C because it goes from C minus minus to C. I'm pretty sure. Uh, so the basically your code will get compiled down to this, and this is actually what you used to have to write. Like in university, they made us write code like this just to see what it was like and to understand like how a CPU works. Um, and then that gets compiled down to
This is
this.
this is making me think of a meme where it's like Carl Sagan talking about like how to make a pie. And it's like if we wish to make a pie from scratch, we have to start by the creation of the universe.
Yeah, yeah, exactly. I'm trying to find just an example of, I mean, binary application code is quite literally
Uh,
like this seems like a meme, but this is actually what your computer reads. Um, and so your CPU, basically, if you have like a 64-bit CPU, it understands that it's basically going to process 64 bits at a time, and then each registry on the CPU, it knows like, okay, if there's a one here, then I want to save, let's say, or if I got a one uh, here, it means that the next operation needs to be pushed up to the stack. And so like it gets very complex. Like the people who wrote this are geniuses. Let's just simplify it to that. But basically these instructions tell your CPU what to do. So the way that this can be somewhat understood by humans is through what's called assembly code. And so assembly code is a list of instructions, right? So each one of these instructions, and you know what? I'm gonna use the one that I understand. We used Motorola 6808 assembly.
Is there many different types of assembly language, or like?
Yes, it's all based on the CPU. Like the CPUs that we have today would use a completely different assembly language. Basically, this language is created by the chip designer. So whoever creates the chip creates the language. It's been standardized nowadays, but I'm just going back to 6808 because that's what I understand. Um, so, okay, this is good, but not quite what we want yet. And by the way, I'm not expecting you guys to like remember this or anything. It's more just to understand like how compute cycles work. So give me a second.
Yeah, Kyle was making a great point in our chats earlier this week, like that we should just start like how does
Yeah,
everything that
there
we're
we go.
doing relate to the low level like what's actually happening in the computer. So we're gonna start to do that a lot more.
Okay, so this is a very simple example. So basically what it is it's a number of instructions. So code segment, this creates this, and this is pushing whatever bytes are in BP, pushing whatever bytes are in DS, moving BP and SP, moving DSES. So this is basically just like moving memory around in the CPU in order to do things. And so certain registries on the CPU will will result in different operations occurring. And so like adding two numbers, like if I can do assembly language addition, for example, I wish I had like examples of this. I wish I still had my university code. That would be, I probably do somewhere, but because they made us just to they made us write Simon Says using only assembly language. Uh, I think like 80% of this class just like couldn't do it, but not to toot my own horn, but I did it. So, but it was hard. Like it's all basically like recursion and these instructions. So, to get back to the point that I'm trying to make, each of these instructions takes a number of compute cycles. So, for example, the integer arithmetic, this isn't a good example. Um, assembly instruction compute cycle. Okay, yeah, here we go. So each of these instructions takes a number of cycles. And so each cycle through your CPU translates to a number of time. There's a way you can calculate this. Um, and so at the end of the day, basically the question is like, how many compute cycle, like Galen was mentioning, like provisioning a new thread. Provisioning a new thread might take, let's say like 2,000 compute cycles, whereas doing 1,000 addition typically takes like one or two, um, like yeah, two here for an and. And then let me just, you can see my Discord notifications. Um,
My bad.
it's all good. Just be careful.
I'm just saying this is like definitely I'm loving what we're doing here. Like I think we need to explain to the low level for every single thing. Like I think that's
Yeah.
how we tie all the different lessons that we're doing together.
Yeah. So for example, adding two numbers together here takes 5 compute cycles, right? Um, and so especially in something like Haskell, you're actually gonna like it's gonna reduce down to this. There's some languages that they try to just like get rid of this concept of compute cycles. I don't know why. There's probably even, and you know what? Just gonna just because if the teacher does it, then it's okay. We're gonna use Copilot. Does any um, is there a Haskell library to calculate compute cycles?
You say it's okay, and then don't use DeepSeek, but use Copilot.
It's just right here on my
I'm just
computer.
I'm I'm
I need to use DeepSeek. Honestly, Copilot sucks, but RDATSC that can be used to measure the number of CPU cycles required for a computation. This library utilizes RDTSC instruction on X. Yeah, okay. So like literally we can, and maybe we can do this. Maybe we can do it today or another day, but we can calculate how many. Yeah, you're basically just. Oh, that's what. Sorry, I love Haskell. Everything in Haskell just comes down to like 2 lines of code when you get like these really smart library developers and they just there we go, just start it and end it.
There's just
Um,
very focused effects, you
yeah.
know.
So there are like all of this to say like there are high level libraries to calculate this. But for example, if you didn't really know about compute cycles, then you wouldn't know to ask this question. And so that's why like understanding the lower level can help you. So all of this to say that like if the operation that you're trying to do to perform takes like more compute cycles than what it does to provision a thread. And keep in mind, you can also thread pools, so you can have a bunch of pools just sitting idle or a bunch of threads just sitting idle in a pool, which is basically like an array. Um, so it just depends on like what kind of benefit you're going to get. Uh, Users will start to complain after, I mean, it used to be 2 seconds, but I would say it's probably after 1 second nowadays. If your application takes longer than a second to respond, it's too long. Um, and there's probably something you can do to optimize it using threading. Um, Other than latency, you can't really get around latency, but
Okay,
yeah,
thank you so much. Thank you so much. That was very helpful.
awesome. Yeah. Uh, any other time that you want any low level stuff, I could dive into this, but it's been a little while for me too. I just understand that your code at the end of the day, like your computer is not running Haskell code, right? Like Haskell code is never going through the hardware on your computer, right? Um, at the end of the day, your CPU can only understand something like this. This is what your CPU reads at the end of the day. And it'd be great actually to maybe one of these times if we want to get even lower level, we can actually take a Haskell program, compile it to C, and then run that C code through an assembler and like take a look at what the assembly code looks like. It'll blow your mind. It's going to be like 10,000 pages worth of assembly,
Yeah.
but that gives you kind of an understanding of like how lucky we are to be able to write code in a language like in a high level language. And it also gives you an understanding of like why certain operations take longer than others because you know atomic operations as they're called are they happen in one compute cycle. So just to quickly close us off here, there's something called atomic operations, and these are operations that occur within one compute cycle. There's only so many that you can do, and when you're doing high performance computing, atomic uh, operations are like the best thing that you can do like atomic addition examples, for example, here. And I believe Haskell has an atomic library, but I don't think we're getting into that
Sorry,
today.
how is this related? I think I missed a step here. How does what does atomic have to do with the overall idea we're talking about, or?
Because atomic operation uses one assembly instruction.
Oh, okay. Got
Yeah.
it. Okay, yeah.
So they're extremely performant. Like typically, like if you're doing, for example, if you are like reading a value from a list, like an array, um, that's a multiple instruction operation. Like it has to first take the memory from that array, move it into a separate buffer, then pull that down into your working memory, and then it needs to perform a read. So it's like at minimum 3 instructions, where like an atomic operation would just be 1 instruction. But I think it's a little too much for now. I'd like to do an example on that in the future. But something to look into is just understanding that everything we do gets converted into these instructions. And so what might look like one line of code in Haskell could be 1,000 instructions, right? And so performance, like you can look at the big order notation of the code that you're writing, but that doesn't mean that it's going to be performant because y like big O notation is great, but it doesn't mean that that what you're writing, like for example, you could have an, a big O of N1 or of you could have big O1, but each operation takes like a ton of compute cycles, right? And so like it doesn't really tell you about the actual time that it will take. It's just like how efficient is your algorithm. Whereas understanding the compute cycles that something takes will actually it'll actually tell you how long it's going to take to perform an action as opposed to just like the way I look at it is big order or big O is the relationship between the instructions you're writing and the amount of time that it's going to take, but it's not actually telling you anything about the amount of time that it'll take.
It's like an abstract concept, really,
It's a
as
yeah,
opposed to like
big O is an abstract concept, yeah.
yeah.
But yeah, let's continue with the lesson there, Galen.
Yeah, cool. I think it's like um super cool too because I feel like as a developer like you're dealing with both sorry, someone's audio is very loud. I'm so easily distracted. Um if they wouldn't have muted themselves, I think it might be you, Hillary. Oh, thank you. Okay, yeah, there we go. So yeah, like I think it's cool because like yeah, like I don't know what everyone is coming in with their knowledge about like the low level of like how stuff actually works. But ultimately, like as soon as you get into like I need to write performant code, it's important to like understand these things at a deep level. Um, I think it's really complex, really quick, but like also too like it's once you understand it, it's actually like wow, everything is really just like these five basic things. Um, like even like for addition, I'm pretty sure it's like the assembly instructions are just like move the bits onto the register, move these bits onto the register, and then like there's a instruction to do addition on assembly, right?
You could say it's simple, but here, I'm going to share my screen one more time just to show everyone what addition actually is on your computer. I've showed you this before, Galen.
Mm-hmm. Kyle, our local whiz kid.
Where is it? I think that is it, but it's not a good example. Yeah. No, that's not it.
Well, it's just like and almost right or
It's a bunch of ands. Yeah, we had to make this circuit in school, and that's why I remember it. But give me a second. There it is. So that right there is what it takes to add one number together. I'm not going to explain it perfectly right now, but basically everything comes down to a number of so these are AND gates and these are OR gates and these are NOTs. These guys here, those are saying NOT. So it's basically just like your CPU, and it's insane how they've gotten these down into like nano. Like there's now like they're like doing nano circuitry with this. You can't even see it with like a microscope. I think it's even smaller than nano now. Um, but like basically electricity comes in and this is how it adds up numbers. So you get your A and B. This is you're adding A and B. This is your carry. So anything that carries over from a bytes perspective, because we're using binary instead of hexadecimal or decimal. Um, and so you add A and B together. You take the NOT of A and the A, and then you and the A with the B and your carry bit, and then yeah, it's I'm not gonna get it. I
Yeah.
low key kind of forget it, but like this is what's happening at a low level. So one of those instructions in assembly is being translated into A, B, and C, and then it's being sent through your arithmetic logic unit on your CPU, and then your CPU is spitting out an answer. So like all of this has to happen just to add one number together, right? And so you can imagine like how much is actually happening for some of these operations that we're doing.
Yeah, and like I mean, ultimately it's just like I remember at a high level it's just one and one is two, and then like like the if the presence of one is true and the presence of another one is true, then we have two, we have a sum. And then like every number larger than two is just like recursive of that. If we have,
Exactly. Yeah.
like
And that's
if
what
we,
the carry register's for.
yeah,
That C there is for everything that goes beyond the two.
yeah. And so like if you
But
have a million, if you're adding to a million or whatever, you'll have like a million carries ultimately.
yeah,
Yeah. So that is the low level CPU.
very high level explanation of the low level of the CPU.
Yeah.
But there you go.
So and that's what we're always dealing with. And so like yeah, what I was saying to Kyle over Discord was just like we'll continue to like kind of try to pull it back down to a low level, because like ultimately it's just gonna help make everything simpler. Like like to unfold this complexity of what is happening at a low level, is gonna eventually have you guys just going like this is the same old stuff, and um, and yeah, so like, and I mean, I'm imagining most people are coming in with like, and this is fine if not, but like, if you're coming from like another program, awareness of like, if statements and like the basic syntax and all that, the basic logic of how to write like a program, is there, but like, how does that all compile down and how does that all actually work? And like, what's actually going on here? Um, but yeah, so like where we were is we were talking about like parallelizing this program, and oh, was that a question or was that?
That's Nick. What's up, Nick?
I was just going to say, if anyone wants to know more about that stuff, there's a really good book called Elements of Computing Systems. But it's like from NAND to Tetris. There's a website for it as well, where you can literally build a small computer
It's blurry, but
virtually on your computer up from NAND gates. So that's kind of
yep,
into that.
it's
So.
exactly it. And you can see how thick the book is.
Yeah.
Yeah. It's interesting stuff. Definitely like a fun project. It's sad we don't have to do it's low key sad we don't have to do that stuff anymore, but also it's a good thing because if everyone had to do that, no programs would be getting written. So
Yeah, and
Take forever just to add any numbers.
Yeah, yeah. Take you a month just to write something that to add a number together, right?
you see like entire venture capital firms on just like raising numbers. You know, like
Yeah,
we don't even know how much we're trying to raise because we haven't gotten that far.
yeah.
So we haven't added it up. Bad joke. But yeah. So now, what the actual intent of today is to talk about is like, so let's say we have these two programs, um, and I'm going to step away from the web server example into a more familiar example that I can actually come back to a bunch. Is I have a web scraper. So I want to do natural language processing with a ton of Wikipedia information. So I have my master program, which is going to the master web scraper. Oh, I gotta change that. Master web scraper, and this is going to decide how each thread should work. And so I can again make them however many threads I want to. Um, and so let's say in this case I make two, right? And so I have like thread one, and then I have just like thread two slash web scraper two. Threads two. Pardon my typing today. My wrist. I went bowling and I'm incredibly sore, so I think I'm just not typing very well. But at least I have Haskell types to help me with that. Bad joke again. But like, so at a certain point, you're going to run into an issue. And I, in this actual case, ran into an issue where these are not easy to parallelize. I can't, like, I can't simply fork the thread and then never have to deal with it again. Because what's going to happen is that I have I have these two threads which the programs themselves are not going to interact with each other ever, but I also have another problem, which is I have some data, right? And in this abstract example, which I'll get into a concrete example in a second, both threads care about this data. And in general, any case where we have two threads which care about some data and are interacting with and reading and writing to some data, we're going to encounter a challenge that is like unique to parallel processing. So, for example, I think a bank is a great example here. Is like, let's say this data says that like Kyle has $1 million to buy the moon. Another bad joke. Maybe you guys get that one. Just full of bad jokes today. And then Galen has, I don't know, $3. And if I let's take two scenarios. I want to perform a function, right? I'm going to perform a function or whatever, where I'm going to transfer $1,000. There's two scenarios in which one will work and one will not work. If I transfer like $1,000 at this current state, then the transfer is going to fail, and we're going to deal with that, appropriately. But then there's another scenario where Kyle says, "You have $3, you broke idiot. Here is $1,000, and then I'm going to be good to go." And the key thing is that right, that change to my data of how many dollars I have to my name needs to occur before I try and transfer it, right? So the sequencing of operations becomes very important here. And in object-oriented programming, like this is kind of like a very unique thing to functional, and we'll see why this like functional is so awesome for parallel processing, and declarative more generically is that like how we think about data and reading and writing to data is differently. So in object-oriented, we kind of think of like this data as being like something that is almost like self-changing, right? Like we'd have like we might have some code like I don't know, bank dot Galen dot transfer, or like debit, or uh, uh, I think debit is like to take out of the account.
Just say transfer.
Yeah. Well, yeah, no, but like transfer divides into
It,
two things. Is my
yeah, usually transfer functions have like a to and a from.
right? Sorry, I'm
That's
stupid here.
probably
You're right. No, you're like yeah.
it'd be like bank dot transfer to uh, Kyle from Galen or something like that.
Yeah, but like ultimately, like the point I'm trying to make here is like that this is like removing or how we typically think of data and object oriented programming is kind of like the data like sort of acts on itself. What's actually happening under the code or under the hood is that like we're applying um, the function of transfer to some data. And even if we like were to compile down the code, like C, which we're compiling down to, is a functional programming language, and and we start to see like this very subtle distinction between the data acting on itself, the data performing an action on itself, versus performing some actor or some program performing an action on the data, coming in handy. And I don't know if that really matters yet, but ultimately it makes it really easy because in Haskell, we have two functions here. One which is write data. These are just made up at the second, and read data. And we'll see what the actual functions are in the context of parallel programming. But like these are functions we are performing, right? And so read data gets the state of whatever is at that moment, and write data changes that state. So, we've established that it's important that transfer happens, at a particular point in time. And of course, this isn't just hanging in the air. This is, or like, just like running on its own. There's an actual thread which is running this function. Sorry. Running this function of transfer. Sorry. There's an actual function. My allergies are coming in strong all of a sudden. But there's an actual thread which is running some function of transfer which depends on this state. And so, not only does it matter, like we obviously want the transfer to work at the appropriate time, but we also want like another issue where like let's say Kyle does two transfers. Can I do that? Yep, there we go. Kyle transfers on like this thread. He's going to transfer 1 mil. And then he's also going to transfer another $1,000. This is another case where we wouldn't want like we wouldn't want an inconsistent state, right? Because there's a world in which our program has a bug that allows Kyle to transfer more than he has to his name. And how that would happen is, like, let's say he transfers 1 million. This reads from the data that, you know, this reads from the data that, like, he has 1 million, and this also simultaneously reads from the data that he has 1 million, and then it for whatever reason we don't check at the moment that we do a transfer. Kyle will somehow send out more than he has, which just doesn't make any sense. But ultimately, what's happened is that, like, we had 2 reads, and then we had 2 actions, and then the actions tried to reconcile, and it made just no sense. We have created $1,000 out of nowhere simply by a bug in our program. What the heck did I just do there? And so, like, the point I am making as a whole is that when we have multi-threaded programs, it's very important that our data is atomic, right? And this comes, like, almost like by default with databases, is that, like, we have this concept of, like, atomic transactions, where, like, let's say, so like what's actually happening with the transfer is that a transfer breaks down into 2 different things. Oh, sorry. Let me do that. It is a debit to Kyle's account, and it is a credit to someone's account. Right? So, like, we take the money from Kyle and we put that money in Galen's account, for example. Right? The debit is taking from the account, and the credit is putting into the account. And so we, of course, always want the debits to equal the credits, and never have an issue with that ever. And so we want to make sure that these always happen together, right? And I think we can see why at this point that we always want them to happen together. We never want one to happen, but not the next, right? Scenario 1 is we debit from Kyle's account, and the $1 million goes missing because we take it out, but we just never add it to someone's account, and the money is lost in transfer. The second case is that, somehow we create $1 million out of nowhere. So yeah, we don't want either of those scenarios. Is there any questions so far, or questions about the logic? We haven't gotten into much of, like, the actual programming yet, but
Yeah, we'll just say in a database, typically this is handled through what's called transactions.
yeah.
And so if any of these steps happen, or if any of these steps fail, then they all fail.
Yeah.
But if you're ever working with money in a database, like, you need to use transactions. I'm pretty sure if you get audited and you're not using them, you can get in a lot of trouble.
Yeah.
Because for this exact reason, like, you can basically just create
Fraud.
money out of, it's fraud. And so, yeah, that's a good example. Now, how does concurrency kind of come into play here?
Yeah.
Just to keep the ball rolling here.
Yeah. Well, so I mean, this is what we define here is a concurrent program, because we have, of course we have, like, this individual transaction. That's how we hope for it to happen. But we also have another transfer going on at the same time. And so, for one, we want to make sure that, like, this happens atomically. But we also, have other programs which are going to be reading and writing from the state at the same time. And so, like, if we go back to our original example of can I transfer $1,000, the answer is only after Kyle transfers me $1,000, right? So, like, let's say this transfer happens that affects the state of this. Um, that means I can then go and transfer $1,000. Just in terms of like the flow of what's happening here, right? If this was to happen and this was like the step one, right? This is step one here, then this is going to fail.
So is the second thread number 2, is that happening, like, is that waiting then on thread number 1? Like, wouldn't this still just be a sequential application, I guess is my thought.
Um, what do you mean by would this still be a sequential application?
Well, because if the second thread can't do anything until the first thread is finished, like, what is the second thread doing while the first thread is operating?
So okay, so like we also got to define what is the actual input to this master server here, um, and more appropriately define what that case is. So like let's say Galen transfer happens first, and then Kyle transfer second. I'm just gonna do this.
So this is like a message queue?
Yes. Like or like what the actual, it doesn't even necessarily need to be a message queue, but like you know like this is just a web server, right? Where like a web server is ultimately going to divide up into a number of threads for each request. So like let's say the web server, I first tried to transfer $1,000, and that is going to run first. Like these threads, this is going to start thread 2 in this case, and then it's going to immediately start thread 1. So both of these threads are going to be running at the exact same time, but this is going to be like a millisecond faster, right? Or like a millisecond ahead of time, and it's going to read from the data first, and then it's going to fail. And then the thread 1 is going to happen, and the transfer is going to happen, but it's going to be irrelevant at that point. If Kyle transfers first, or like the request is received first, and that thread is started first, then the thread for Galen is started second. This thread and this thread are going to be working at the exact same time. This will be a millisecond faster, and this will get access to the data first, right? And so,
Not necessarily.
what do you mean?
Like, I don't want to, but I think this is important to mention, that this would technically be a race condition because.
Yes, if it depends
So
on the program that we're working with. If we're using Haskell, then we
exactly.
avoid
So
that.
that's what I'm kind of trying to urge you towards, is like, in typical threading, this gets into the, like, and you're correct, Galen, but I'm just saying that, like, in a typical language that doesn't handle concurrency well, what you would have here is a race condition, because you can't guarantee how long, especially if there's any latency involved, like especially on thread 1, like where these transfers, those are going to be side effects, right? And so, like, literally there could be, like, the amount of time that it takes is going to be different every time because it's a side effect. It's not a pure function, right? So these threads are not pure because they are transferring using some bank API, or even like a call to the database or whatever. If these were pure functions and you were using atomic operations, then yeah, you could guarantee that one thread will happen before another. But in this case, we can't necessarily guarantee that. So this is enter the room, software transactional memory.
Yeah.
Right? Where now we're looking at, okay, how can we have both of these threads running at the same time, but have thread 2 only run when thread 1 is successful, right?
Yeah.
And that's where something like STM comes into place. There's strategies for that, like mutexes and semaphores you might have heard of, which is basically like a talking stick that you hand around. And so if it's not your turn with the talking stick, then you don't go. But STM is a better approach to this. So I guess it's a good point to ask, does anyone have any questions about like the problem that we've kind of identified here? The problem that we've identified is that thread 1 and thread 2, we don't know which one's going to end first, but we know that thread 1 in this specific case, keep in mind that the data, like this could be switched around. For example, Galen could have $1 million and I could have $3, or neither of us could have $1,000, right? And so this thread 2 is very much dependent on the state of the database, and there's other threads interacting with the state of that database. So how do you handle this? I guess is a good question for people in the chat. Like, are you understanding the problem here? And if there's any questions, I'd be curious to know. Olajide, yeah, go ahead.
Yeah, so my question is there a way to prioritize 1/1? And also, wouldn't that cause some kind of, because the overall idea is for us to not experience any kind of lagging. So yeah.
Yep. So ideally, the user, so what you wouldn't want is for the user to basically just be wondering what's happening, right? Like, for example, if the user is waiting on the transfer to occur to like the transferring $1,000, you would want to tell them, like, please wait, this is where the thread can actually report back its current status of like, oh, well, I'm doing this first and then this and then this. You know, you do have to wait on threads at some point. Like there are cases where you'll have to wait, but Galen, do you have a comment on that?
Well, yeah, I think like there, I think the ultimate strategy is just exactly what STM does, which is literally just you have to wait. Like even if we have of course there's the normal program, the typical program which like has race conditions, right? Where we have some mix of these four like actions being mixed together, right? Is a race condition. Um, of course, we have this and this. We want those to be atomic, and then it really comes down to like what do we want to happen, right? Like as an actual like programming and like application logic, what do we want to happen?
What does the business want?
Yeah, there's never a case where we want a race condition because that like just like it doesn't exist. And
does everyone know what a race condition is? That's probably a good place to.
Is it an issue where it's like a race, in other words, and it's whoever's first come becomes first come, first served, even if you didn't want them to be first?
Exactly. So it's basically it's a race condition it's usually results in a crash, or in some kind of failure in the application that you're not expecting, and they're usually very difficult to solve, because it's exactly that. It's a race to whoever gets there first. So especially when you're dealing with side effects, like this is why we like pure programming so much, because when you're writing in pure code, you never have to deal with race conditions, because you know how much each like every time you run the application, it's going to do the exact same thing. So if it's 100% pure, you're not going to have a race condition. Where you get into race conditions is when you've got things that can end execution at different times every time you run it. So interacting with two threads, they're not always going to end at the same time. They're not always going to start at the same time. And so every time you run the application, you'll get an error. There's some race conditions, for example, where the issue will be solved by adding in a print statement. So you'll be right. So you'll have code and then it works, right? And then some developer 3 months later adds a print statement somewhere in the code, and that print statement causes the function execution to take like half a second longer. And now all of a sudden you're getting a different result.
Yeah.
Um,
The key thing is that it's just not declarative. Like ultimately,
yeah,
like it's not even. I don't think random's even like it is technically random, but like
random to
more.
us, but
Yeah,
yeah.
because and random to us is like ultimately this is just not declarative. I never said like look if we look at this like I'm making a race condition here. I am forking so in this code I am forking 10 different processes, which are all going to print what number it got. And so this should, in a sequential program, print 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? If I do that, let's just easily do that. That's what it looks like. But if I add in, and this is how you do it in Haskell, by the way, is you fork the program by just literally using fork.io. It could not be simpler. We get some like chaos here. I don't even understand why this. Oh yeah, this is 10. So like not only are these 10 different programs that we forked, trying to write to the buffer, but so is our REPL.
Yeah,
And
yeah, and that's really interesting actually. The REPL thread is ending before the 10th thread.
yeah,
That's why you're seeing the what do you call it? Those three lambda, like the green text is cutting off the 10
yeah. This is just
because it literally,
my prompt. Yeah,
yeah. And so that's a perfect example actually of what a race condition would do. And
yeah.
you see it's different each time.
Yeah, and so like we obviously don't want that when we're talking about like a bank is a great example because we don't want like chaos when we don't like I don't want to transfer money and then like one time I transfer $5 like 7 times and then one of those times like I end up with like -70. Like how do I like or like just some crazy random seeming condition that's ultimately just a result of a resource being used by two actors at the same time.
Yeah,
Was there a question there?
yeah, Nick.
Yeah, so I was just going to ask. So, is there a thought also about in your example where you have the two threads? If they're such small computations, breaking them and they both have to regularly read the same data, is there a question of then does it just truly becomes sequential again, if you know what I mean? Because if they're both having to read so regularly from the same piece of data, they're effectively got to wait for each other at every point. Or is it that fact that when you get low level, for most things, there's so many computations anyway that even things that seem quite small will parallels for quite a while because there is quite a lot going on there. Do you know what I mean?
Yeah, yeah.
Yeah, I
So
know what you mean.
the way
Yeah, go ahead.
I think about it is that like when we like even in the context of a concurrent or parallel program, data should still be sequential, right? Like if we if we think about this as like a database server, even that server, like maybe it's like creating like a message queue of like requests that it needs to respond to. It's just simply saying like, okay, I'm going to deal with request one, then I'm going to deal with request two, then I'm going to like, and there's no at this at this point in this domain or like this subdomain, everything has become sequential again. And that's what we want when it comes to data. Um, like because like the question is like so we know that we want these two things to be sequential or sorry to be atomic. We want them to happen together, and we know that we want these two things to be atomic and happen together. But which one do we want to happen first? That's like there's not like a more there's not anything that makes more sense than just to say the order in which they were received. Um, and like even in the context of it's theoretically possible that even if Kyle's request is received first, and then my request is received second. So you would think, based on our example, that um, the my transfer of $1,000 should work because I've been given $1 million by Kyle, or some amount. I forget what the example was, but like, um, then that should work. All things assumed to be equal. But like, let's say Kyle has like a flag from sending $1 million, and this will literally happen if you send enough money, through a bank. They're gonna say, "Whoa, like what's going on here?" We're gonna like do some deeper processing, um, and so thread one might have started, let's say a second prior to thread two, but if one has some logic that like has some like pre-checks that it needs to do before changing the data, then that is going to mean that thread 2 is going to affect the data first. And so it's not guaranteed that like um, just because my thread came in second that it will succeed, right?
Yeah.
It really depends on um, like what actually reads and writes the data first. If we look at from the data level, right? If we were to ask like as simply as like there's like one simple function we have, or we have two simple functions, read and write, and read and write. Um, but at that point it's simple. Like we can say that like if Galen tries to affect data first, he's going to fail. If Kyle tries to affect data first, the entire thing is going to succeed, right? Kyle's going to succeed, and I'm going to succeed. Um, and so, like, the thing is, like, it's not perfect, but like, what could you possibly do better than saying, um, like, there's no magical solution to that. Ultimately, too, like the user can probably know that okay, I haven't gotten that transfer from Kyle yet, and most times in reality you're not trying to transfer the millisecond that you get the data. So like what's more likely to happen is that like Kyle's going to transfer $1 million. I'm going to go to my UI. I'm going to see, oh, I got $1 million, and I'm going to transfer $1,000. So there's not like, but so ultimately all we can do is just say handle requests in the order that they're received atomically, right? That's the ideal design to a parallel or concurrent program.
And keep in mind that it's not like we're choosing to multi-thread this. It's in the design of the fact that we're dealing with multiple people's requests. Like because one request is coming from Kyle, one request is coming from Galen. The web server actually has to split this out into two threads, because if it was just working on one thread, Galen's request wouldn't even go through.
Yep.
Right.
Okay. So yeah, so sometimes you're forced into multi-threading, even if you would probably want to deal with it sequentially. So this then allows you to effectively sequentialize something that is running in parallel.
Exactly.
Yeah. Thank you.
Just trying to find where I have.
Yeah, the world is not sequential, right? Like we're all like, it's a good way of thinking about it is like my brain is operating separately from yours, right? Like we're different sentient beings and we're interacting with this program. And so because of that, there is inherently asynchronous behavior in the program.
You're assuming that I'm sentient. Kidding. Yeah. So like, I figured too. Like, honestly, we could even make this really simple, and just like, I'll show the program that I actually use this for in the end. But like, let's actually like write this program for a bank, because a bank is actually quite simple. Which you wouldn't believe if you looked at their legacy code bases, but that's beside the point. Let's say our bank start is well, I'll just write a data type for this so we can think about this easier. Bank equals bank Kyle has an int, which of course I know it makes more sense to have a float here, but I don't care. I think we get the idea.
Technically, you would want to do a rational money type because floats are unsafe.
Not a float, definitely not a float.
You want to
Definitely not a
yeah,
float.
you definitely don't want to use a float for money. But anyways, we'll get into that later.
Yes. Okay, so that looks good. So now all I need to do with this is, well, let me actually make my first instance of bank. Bank start is going to be bank, and I can just define this by saying Kyle has 1,000 and I have $1. I'm thinking of the Patrick Star meme where he's like, I have $5. Maybe no one gets that reference, but so like to make a TVAR is very simple. So all we have to do is we have this function. Where is it? I think it's new TVAR. So yeah, new TVAR. Oh, you know what? I should definitely open up the. Yeah. So like, this is the actual module for. No, that's not what I want. Contents. This is the actual like package for dealing with like software transactional memory, and so like this is just again like almost like this is exactly implementing the ideal design we've talked about, right? So we kind of talked about like what could happen with this program going wrong, and that's what you'll ultimately see in a lot of other programming languages is that stuff can go wrong. But yeah, in this case, we have software transactional memory, and it's like literally there's nothing you could possibly do better than this this package. So we have like this like STM monad that we're going to be dealing with, which is actually, if you look at the implementation of it, we won't get into this today, but like if you want to nerd out, is very similar looking to IO, and yeah, like the implementations both look very similar, and you'll understand why with a bit of like research, but I won't get into that today. And there's a core function we have here to run this monad, right? And we'll maybe you're not familiar with monads yet, but we'll see the point of them in this example. But we run any transaction, any STM transaction using atomically. And so this just, what does this do? It tells us right here that this ensures that every single thing succeeds or nothing succeeds. It's all or nothing. And that's what is meant by atomically. And yeah, and then like the other where is TVAR? There we go. So TVAR is our actual like transactional variable where we can store information, and so the kind of like base way to do things is that we can create a new TVAR, but I'll just show you guys with new TVAR IO here that it's really as simple as this. Then we say bank start, and we can check the type of this. We can see that it gives us an IO of TVAR bank, and what this ultimately is a reference to this shared memory location. And the only way we can interact with the shared memory location is by this library here. And so what can we do? Well, the two core things are we can read the TVAR, and we can write to the TVAR. So we can write a new TVAR to that location. So like for example, how would I do this? I would say atomically. Let's read it first, actually. Atomically read. Oh, I need to bind the variable first. So I just threw out the value, my tvar. And so now we can see that the type of my tvar is a tvar bank, meaning that this will fit into tvar A, and will give us back, if we apply, like, we apply read tvar, we see that this is a STM monad action that gives us a result of, or gives us a bank value. So, and ultimately, like, what this means is that I can't just, like, the point of the STM monad is that I can't just do this. Well, I mean, I'm trying to, let's say I want to print out the tvar just very simply. I'm going to say read tvar, and this is going to give me an error here. It's going to say that's the wrong monad. This is the wrong context, and you haven't dealt with the STM action properly. And so, like, the way that we would do this is we would say atomically. Yeah, we don't have a show for bank, so I guess I gotta. But you know what? I guess I can do. I'll fix my sins here by saying print Galen. Okay, so that we run the atomic action of reading the tvar, and we print the well. Let me simplify this a bit here. If we run atomically, and we get our bank new, right? We see that the type of bank new is just reduced to a very simple bank again. And if we then ask what is the balance of Galen in bank new, we see that it's 1. If we ask the same for Kyle in bank new, we see it's 1,000. Does anyone have any? Oh, does anyone have any questions there?
No. And so, I guess if I were to come up with a question, what would be the difference? Because you show that we can't just run an IO action, right? And I think this is extremely powerful. But maybe can you explain that a little bit more as like why we can't run an IO action, why we wouldn't want to just run an IO action? Because I'm guessing that would, if that would lead to like that, this whole STM concept is what's bringing us into the world of atomic programming as opposed to just having race conditions.
Yep.
Is that correct?
Um,
Because IO, like you
yeah.
just make you just make a request to outside and it comes back whenever, right?
Yeah. Ultimately, the reason is just purity. Like at the end of the day, everything in Haskell is pure except for IO. So we want to ensure that dealing with you know we just want to limit the amount of things we're doing in STM. STM is not meant to be able to do anything besides getting and putting the data. There's just like it's just, I mean, at a certain level, like I'm sure there's a way, we can even, it's in theory possible to do IO in STM, but you just like you wouldn't do it. Like you wouldn't ever want to do
No,
it.
you just have you would have the cache handled or like the data handled by STM, but then you would use IO to like affect that STM cache or something. Like if I have some memory, like how would you, I guess, make a database request like concurrently and have those values still run atomically, I guess.
Well, we're not using
or
a
not run?
database, or like, sorry, like, do you mean like the
Like if there was something that was affecting these values, like we got 1 in 1,000, but those values can change. You would change them with STM, correct?
No, you
No.
would so like, okay, so I have, like, let's say Galen's balance here, right? Like I'll just say G1. I do some logic to it. I debit it, and I'm gonna say that this is G1 plus 1,000. The government gave me $1,000. It just came out of nowhere. They printed it. Let's say that's what just happened here. Now I can write to the TVAR. So I can say, how would I do this? I would say atomically write
Right.
TVAR. I have my reference here, which is my TVAR, and I just have the A. So I guess the I would have to wrap the bank again. So I would say whatever your balance is. So Kyle of bank new and G2. So that's how I would do it. Like, so the point I'm making is that, like, I don't need atomically to do addition. I don't need atomically for anything besides reading and writing to the data. Like the actual, like, discrete action of reading and writing to the data, I already have the
Yeah.
power to do that with Haskell. So, like, why would I ever want to say, like, in theory, I've done like a pure thing there, right? So I could say, like, let G3 equal G1 plus 10,000 in. I don't know if this will actually work. I'm gonna wrap it in brackets just to make sure. G3. Yeah, so I could say that, but, like, I can't I can't do IO in there because, like, IO is the only I think, like, and you can do almost anything besides IO. That, like, and the reason for that is just like why would you want an impure action in reading and writing to a data type?
Mhm.
We got a question.
So, is it? Am I right in saying that atomically is allowing you to do, as in, like, when you were saying you don't want to credit and debit two things, uh, it basically forces that to happen in one go, and if one fails, then both things fail, and it just doesn't happen.
Yeah.
Or does this actually do anything with the bigger picture of sequence? Do you know what I mean? Like, the bigger picture of you've got multiple things working on the STM as well. Do you know what I mean?
Yeah.
The main data.
So,
Yeah. So
like,
if you had multiple, I guess the question is like, what if you had multiple threads all running the atomically on the same TVAR?
That's it.
yeah. So, like, if we had
Right.
something like, atomically. Actually, I'm stupid. I could have just done this. There we go. Program equals atomically. I'll show a real example of this in a second. But we have, yeah, like, read tvar. And this is gonna get X here. We are going to say, like, yeah. So this would be of the type bank. We are going to say. Just trying to think of an actual example, but I think I'm overcomplicating this. If we then if we Kyle has 1,000, I have $1. And we do transfer from Kyle to Galen. Or I'm even just going to say this. Like, we haven't actually made this transfer function here, but we could write this in a second. But, like, I'll keep it abstract for now. And then we try to say, or, well, actually, this will work because Kyle has more money. But if we say then, instead, transfer Galen B to Kyle, then this is not going to work. And like, of course, we're doing this in like a singular transaction here. So like, or actually, no. Even a better example is just to do one singular transfer that will fail. So like, transfer is going to break down into transfer is going to take a bank, and it's going to return a bank. So transfer, or I guess, let me just do this. Yeah, we'll take a bank, and we'll take we'll take two functions. That's, I guess this would be, my brain's just not working right now. Oh yeah, they would take a bank and return an int. Bank and return an int. So, and then I guess we'll have an int here. This will be the amount that we transfer from 2, and this will just be that we're going to check let Kyle equal from or let the amount from be from bank and how do we do this? Okay, so we're gonna reconstruct a bank here. I mean, we kind of need to know what fields we're actually accessing here, but like, so maybe the data structure is not the best to deal with here, but like, we could write this in a way. I'm not gonna worry about the logic for now, because I kind of like coded myself into a quick hole here, but like, this is either going to like succeed. Oh, say okay, case amount from is less than the amount to transfer. Of true. Then we're just gonna like return, an either. Right, bank with the appropriate fields, which I don't know what they would be, or I can't write this in a generic way, because of just the way I've written bank. It'd probably be better to use a map here, but I'm gonna have either a string or a bank, and I would then just say, like, in the case um, of transfer, I could just say left, like it failed. Then I'm just gonna say, what's my fail function here? Throw stm. And so this is going to result in the the program failing as a whole, or I'm going to succeed in a certain way. I wasn't really prepared with this example, as you can probably tell, but actually, sorry. So then, if this does succeed, right? So we have a bank here. Then we are going to say write tvar to my tvar, and then this is not a good example, I'll admit, but like ultimately the point I'm trying to get at is that, like, if anything in this fails, the entire transaction will fail. Let me actually go to a real example here. Yeah, so this is a web scraper that I have, and so, like, I have a list of categories that I wanted to scrape, and so, like, each individual category needs to be, like, sort of sequentially pushed forward or whatever, but there's no reason that I can't speed this up by making it into a parallel program. And so, like, what I've done is, like I have, like, a list of, like, history, math, science, etc. And each individual program is going to start, and then it's going to get the genre that I should work on next. I called them genre for whatever reason. There's some backstory to that, but where was it? Right. So this is going to read in the entire tvar, the list of the tvar, and then it's going to write the tail. Right. So in this case, it would take history, and separate out history from the rest. And then the tail would be, math and science. And so then it will return back to me the head, and then just write this to tvar. So, I mean, that's actually like a pretty simple example, but a real example. Yeah. I'll admit, I definitely butchered this example here. But yeah.
That's okay. I think from a theoretical standpoint, it was good. Maybe take some time, and like it'd be good to see the us to actually do the, what is it? Like the bank transfer example, like
Yeah.
to show the race condition happening, and then show the solution to the race condition. I think that's probably the best
Oh, that's a good point.
best
Yeah.
way to do it.
So, like, like, well, sorry, actually, can you repeat that? I think
I
I
just
misheard
mean,
you.
like, take some time and actually like create the example for the it called? For that banking, like, go back to FigJam. Like actually write this code
Okay.
because I think it'd be good. Like we kind of came up with that together, like on the spot. Probably be good to close some ties because I'm sure there's a lot of questions. We probably made more questions than we answered today, but that's okay. I think that's good. We want to get people thinking about what this kind of like what this is.
Okay. Well, I mean, ultimately, this is like what the program is. Like, it's not anything more complicated than this. Like, I ultimately I just used a bad data structure. Like, bank would be better to be a a map of like string to int where we have what's it Kyle has 1,000
Mhm.
and Galen has $1. Um, and the way that like there's kind of like what I'm realizing too is there's a pure way to figure out like what this is doing without it being an atomic transaction. You don't even actually like necessarily need atomic transactions for a bank, is what I've realized. It's like it's kind of very simple logic. Pardon me, but 1 second, sorry. If we wanted to write this in a way that takes advantage of like atomic transactions, we would say that like transfer is instead let's call this transfer prime is going to be instead do debit from to or sorry debit from credit to and this is what transfer is going to do. Um, I'll need a bank close bank prime and the type of bank prime is a map of string int I'm just going to get rid of this here. Kyle, can you mute with the keyboard?
Oh shit! Sorry.
All good. Okay. Debit amount from. So if we want to think of them as like individual transactions that we want to atomically tie together, this would be how we actually write the high level of it. Right. So we have a transfer which breaks down into a debit and a credit of the same amount. And one is going to debit the account it's from, and the other is going to credit the account it's to. Debit meaning take, credit meaning give, which is backwards in my mind, but is how it is named. So debit is going to take the int amount. Oh, actually, I also need the bank as well, just so I have access to it. Bank amount or string of the name, debit. So in order for this to like actually be doing anything significant, again, we've written a better program here. We don't actually necessarily need atomicness in this context, but like in terms of the bank example, the first thing we want to do is we want to get our bank, and so I'm again mistaken here. This would actually be a tvar of bank. We wouldn't have the bank, but we would instead have a reference to the bank. And so we'd say bank is read tvar of b. We will, how do we do this? If we, I think it's map.update. Let's actually figure out our function here. Yeah, okay. So map.update, this is going to take a function which takes an A and returns a maybe A. The A is going to be the value of the map, and the key is going to be the second argument, and that's going to be the what we want to affect. So I'm going to write that in for now. That's going to be our function. That's just a typed hole, by the way, because I don't know what I want to write for the function yet. And the let me just do this actually. The from is going to be the key that we're going to be affecting. Bank is going to be the map that we're going to be acting on. And now we can write our function. So our function is going to take the value, the amount, and I'm going to say amount debit, amount minus amount debit. And then I would, of course, well, I'm just trying to think about how do we fail here. Well, I guess we could do a check first. We could say, let me just do this instead. I'm going to do map dot lookup at the so yeah, map.lookup, we take a key. So the key is going to be from, and our map is going to be bank. And I will say case map.bank.lookup is nothing. I just do fail str, or how do I actually fail here? Oh, I can just
What do
say,
you mean by fail? You want to throw an exception or return a?
yeah.
Probably don't want an exception, right?
Yeah, I actually do. In this case, because like this is impossible. So I mean, I guess I could like, maybe there's a better way than throwing an exception, but I'm going to throw an exception here. Instead, I'm going to make up some exception here. Yeah. So that's yeah. We have tried to debit something that doesn't exist. then we're going to throw an exception. If we did find the value, just amount. We're going to say case the amount is less than the amount we are looking to take away from it of true. Then this is this is going to be an error because we are trying to debit more than we actually have, and so we're going to say throw SCM my exception, and we could have, of course, better exceptions there. But in this case, we'll say, so in the case of it being false, that we actually have more money than we're trying to debit, we are going to then say write to the TVAR. So write TVAR. We're going to write to the TVAR the updated map, and so the updated map is going to be I'm over here. Update. That's going to be the update function that we're going to use. So it's going to say map.update. Not sure what it is yet. Our key is going to be from, and we're going to update the bank, which is our map here. And so amount, and this is just going to be just amount minus amount debit. And we're returning a just here because for whatever reason the update function takes maybe, and I guess if nothing, the element is deleted. So we could, in theory, delete the entry in the map if we wanted to, but we don't want to do that. We just want to debit from the account. And so we're going to write to the TVAR B new bank. Right, and so that's an individual debit function that we have here. And so for whatever reason we've chosen to write this as one individual transaction. And we can do the same with credit. So credit is going to be a lot simpler. Credit is going to take the same types. It's going to take a TVAR to our bank. It's going to take the amount, and it's going to take who this is going to. So let's say B amount credit and 2 is going to be due. The first thing we always need to do is read the TVAR. So we'll say bank of the type bank prime is going to be read TVAR at a reference. Case map dot lookup from bank of nothing. So we can't debit to someone who doesn't exist. Or maybe they do exist. Sorry, maybe it's not a problem if they don't exist. Maybe this is the first time that they're being credited. Like we have a blockchain and a new user has joined, and they're getting their first transfer. So instead, I'm just going to say let new bank equal. We have an insert function which I believe handles if the key is already present in the map, the associated value is replaced with the supplied value. Um, so instead I'm gonna use insert with, which is a little bit more generic. This will just replace whatever there. So that obviously won't work if I want to say for a user that has $1,000 and they get a transfer of $10, the end value that I want is for them to have $1,000 and 1,010 instead of just $10. So I don't want to replace the value. I want to update the value with a more generic function. So I'm going to say insert with map dot insert with. And this is going to be a function which takes two values and gives me something else. I'm going to act on the key given by 2. And I guess this is the new value. Okay, so the new value is the amount to credit. And finally, our map that we are acting on. So how does this work? This looks like the new value. Wait, no. I don't think it matters. You know what? I'm overcomplicating this. In this example, it doesn't matter because we're just going to be adding them together. We are literally just going to put A plus B. So I believe this is the old value and this is the new value, and we're just going to add those two together. And that will give us our new balance for that individual user. And we all have our new bank value. And so now that we've done that, we're just going to say write tvar b new bank. Right? And so now we have something that we might actually find interesting to do atomically here. So, like, if this fails, right? If debit fails, then so does credit. Does that make sense?
Yeah, and so if one fails, the other fails, but also it means that if someone starts doing a transaction, it's locked, and I'm guessing it's locked into that TVAR. That TVAR is locked from only one else really accessing it.
Yeah.
So you effectively create that sequencing effect, even if
Yeah.
lots of things are happening asynchronously behind. Yeah.
Exactly. And you can imagine if any of these operations takes a certain amount of time, the var is going to be locked between the time, I believe, Galen, right? Between the time that you get it and the time that you set it.
Sorry,
Does it
come
lock the
again?
value? Does this function, because I'm still a little new to STM, does this function similarly to like a semaphore in the sense that you're like locking the variable while you're using it?
Yeah.
Like it between the time, is it between the time that you read and between the time that you write, or how does that work?
No, exactly. So like, that's an awesome question because we can see we have this function retry. So like, um, this like this is a bit confusing here, the actual explanation, but like ultimately, what happens if we can't compute the transaction is we can just retry. And so like under the hood too, if this fails, like if it fails to, I don't need to think so much about like what happens if something is already accessing it. Like the library will handle that on its own. But ultimately, yeah, like if one thread is already accessing, running atomically to access some TVAR, then I can't access that TVAR until with another thread until that thread is done with that TVAR. So it's basically the same concept of a semaphore.
And
where,
by done you mean as like once it exits execution of the atomically function, like once atomically finishes.
Yeah.
So it's gonna move into the monadic context of STM. It's gonna do whatever you define inside of that context. And then once that finishes, it unlocks it. Is that how that works? Or do you have to manually unlock it?
no, it just automatically unlocks it.
Okay. So atomically is locking, doing some action, and then unlocking.
Yeah.
Effectively.
Yeah. So
Okay.
like, this, for example, this is forking 5 different programs. Right? Yeah, this is literally forking 5 different programs. This is actually valid code. I just realized it's kind of crazy because you would never write this, but this is going to end up working in order. Like, right, and we can say this for sure because we have a very simple program. We know that, like, there's no complexity to really think about. It's just doing a transfer, right? It's just debiting, crediting, and making sure that it's doing that in order. So, assuming that all of these have the same startup time, these are going to ultimately run and affect the bank in order. And so I actually would need to have, I guess I should make this complete by saying, um, sorry, let me just, I should actually make my TVAR just to show how this works here. TVAR, but yeah, you're ultimately right that, like, if if um if one program has access to it, it and, like, one program already has access to it, right? Like, if Kyle and I are threads, I think of, like, threads more simply in, like, people. Like, I think, like, let's say these threads have come to life and Kyle and I are now
String theory.
string theory, yeah. Kyle and I are threads, and we're both trying to access talking at the same time or whatever. I mean, I guess of course we could talk at the same time, but, like, you know, like, if there was only one, that's a bad example. If there's only one, like, audio that was able to come through, like, let's say Jitsi, literally, like, if someone's already talking, it just, like, muted everyone else. That's a better example. It's, like, impossible. Um, you know, it's each individual person is just going to start trying, or, like, kind of retrying every couple seconds, to access the talking stick, or, like, the semaphore. And so, like, yeah, if you're familiar with the concept of a semaphore, it's exactly the same thing, or the exact same concept. And so, okay, we can say bank. Oh, actually, we already defined bank here, so I can just say bank, right? This is our bank value here. And I'm even going to just, yeah, I'll keep it there. We have our bank TVAR. Transfer bank TVAR. And I guess I gotta give it, like, amounts here. So, yeah. So, like, let's say, for example, I tried transferring $1 to Kyle, 5 times over, and this is actually technically how it would work, because let's say this is a web server. The web server is going to take my request. Like the master program of the web server is going to take my request and fork a thread to process that request. And all it's going to be doing here is going to say transfer 1 from Galen to Kyle. And so this first one is going to run. It's going to have no problem because it's going to call transfer. Transfer is going to start by debiting. Debit's going to realize, yep, Galen is able to do that because he will still have. Actually, I'm just rethinking my logic here. Yeah, we're good. Okay. Galen has enough to debit. That brings his total to 0. And then now I can run credit, and credit can't possibly fail in the way that we've written it. So transfer as a whole will succeed because debit succeeded. And credit will only happen if the debit happened because we are running this atomically, right? So that all succeeded because everything in there succeeded. Now, at this point, all of these programs, like let's say I'm like the literal program running that logic. I've just ran through it with you guys and done all my checks. The other 4 programs have already started up, and they're in queue waiting to read from the bank TVAR. And so I then say, okay, I'm done with it. I don't actually have to say anything besides atomically, but under the hood, the TVAR is released, and I am allowing other threads to access that. So then this will run, and it will try to do the exact same thing that I just did. With the state that I have left, right? So I've left a new state, and now it's going to start with that new state, sequentially about that state, even though it's a multi-threaded program. And it's going to, again, do the exact same check. It's going to see, can I debit from Galen's account? And it's going to go, whoa, I cannot do that. Galen has no money. This is not possible. And debit is going to fail. And so credit will also fail because I'm running this atomically.
But if so, let's say so each of those fork IOs, running atomically. Let's say the transfer function does a hell of a lot of computations in the background before it even touches the actual TVAR. Would that mean that each of those forks could do all of that all that other stuff first, and then effectively just touch the TVAR, touch the TVAR, touch the TVAR, touch the TVAR, effectively making it all still very parallel, but never coming out of sequence when they're actually touching that TVAR? Or does the atomically force it effectively to become sequential for the whole thing? Do you know?
Yeah. I think I jumped ahead before
I think it would depend on the way that you designed it.
Yeah.
Right.
So
Everything, to my understanding, everything inside of the atomically block will effectively wait. Like, that's a good question, actually, Galen. So
yeah.
would the like yeah, okay, so adding the sleeps helps. So would it sleep it would sleep 10, sleep 7, sleep 5, all of those would start at the same time.
Yep.
Or so basically what you're doing is you're starting threads at different times here.
Yeah.
Right? But then
Or
inside of
no. Sorry, we would be.
or you're starting the thread at the same time, but you're starting the atomic operation at different times.
Yes.
Yeah. So basically, yeah, anything you do before the atomic block, to my understanding, would just happen in parallel. And then inside of that atomic block, it's going to be whichever one starts first will run.
Yep.
But you're not going to get you're going to get the same amount. You're going to get the same behavior each time. As opposed to if you were to just basically here we're forcing like think about the sleep as like a pure function, right? Where it's like you do some processing and it takes 7 seconds. Um, it's technically pure because it means technically impure because it's sleeping, but like it's gonna sleep for 10 seconds each time. And so here the they're always gonna start like that last one there, the sleep 0 is always going to be the first to start. The sleep 3 is always going to be the second to start. Sleep 5 is always going to be the third to start.
Yeah.
And so your 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 application will always run in the same way each time. Whereas if you didn't have those sleeps,
Well,
it would
not
basically just be
not
sorry?
necessarily. I mean, like because you could have like in this case where like it's a simple example like of like just sleep. That's true. I like
Yeah, no,
you could
I
have
know. Yeah, that's what I'm saying. In this case, like that's why I said pretend sleep is pure. If this was pure, then we know like it's probably going to take about the same amount of time each time to execute. But if you add impurity in there, then they're going to start at different times.
right. Yeah. Um. Yeah. Like it really just comes down to like the program logic that you have. I mean, like you could even have like um. Well, I guess like in Haskell it's a bit weird because like I was gonna say like technically like you could have like different execution times with like um with with purity, but like ultimately because it's lazy, um
Right,
it
right,
wouldn't evaluate yet, right? Like we could say for example, let my sum equal the sum of 1 to infinity. And like if we were to ever there's two cases. We do this where we never use my sum, and then we also do print my sum. This will like I mean, you know, this will never happen because it's infinite. But let's say it's like some crazy high number. This will obviously take a long time. But what's interesting is that like it's not even necessarily just because it's a long time. It's actually Kyle's right that it is because of the impurity, and it's the impurity that causes the result to evaluate. So we're never going to even we're just gonna like ultimately write this to memory to the stack as like, hey, we need to run this at some point. We need to total this up at some point. And then when we say print, it's gonna say, oh crap, I better do that now, and it will.
and not to add another element of complexion into this, but something to think about is, and I'm thinking about this now, is because of laziness. The first time this happens, it's going to take a lot longer than the second time this happens,
Yeah,
right?
yeah,
So
yeah, and it's
that could also be a source of like things happening at different times, starting at different times.
right. So it's interesting because like there's definitely even still a lot to think about. Like we can't guarantee. We still have to like think about like are we ensuring that our program logic um, is is executing in a proper order. So like let's say I don't think a bank is a good example here, but like if with the web scraper for example, that's a case of like the actual computation takes a long time because the scraper will take the search term that it should scrape um, and go do it'll go do a network request and a whole bunch of other logic and analyze the page. And so like the entire thread might have a lifetime of like 10 minutes. Um, but I still have to deal with like parallel processing. So the the to make sure that my program um, is you know is clear in what it needs to do. The first step that I should sorry, that it's clear in how the program will execute, the first thing that I should do in that case is get the genre. Right. So like, let's say like there's, you know, my scraper it needs to do three actions. It needs to get from tvar. It needs to do a bunch of initial setup, and it needs to actually go scrape and then analyze results. It'd be, you know, let's forget about these two for now. But it'd be important to think about like, what should I do first? Should I do a bunch of initial setup, or like get from tvar first? Then I would say like, to make my program, it's not going to make a huge difference again because it's something that can be easily parallelized. But the first thing I would want to do is get from the tvar, and just so that I know that there's not any unpredictability with like how many different threads are reading and writing from the tvar. I know that like, as soon as the thread starts, it will read from the tvar, and then continue on. And the ultimate reason, like, I'm trying to think of like, why would I want to do that? Why would I want to care about that? Might just simply be debugging. Like if I have, if I'm surprised at like the result that it's getting from the tvar, that like, I'm like, how did this like thread start and then like get something that seems like way too down in the queue, or maybe like, for example, there's like one scraper that is like really quick. Like let's say like going for like history results in a very quick turnaround. And I see that scraper continues to pick up the next and the next and the next, whereas like a thread which maybe takes a little bit longer, is taking a surprising index of the list that I'm not expecting. I'm not making a good example here, but like ultimately, I think what this is saying is like, just, it's best to like try and deal with the tvar, or to like limit the time and predictability of dealing with tvar, because like ultimately, it's not like we're explicitly like programming in how long each of these things should take. We are literally explicitly programming in how long this should take, but we have no idea, looking at my sum, how long it should take. And even further, like, how long my sum should take is machine dependent. Like if you're on a Greek computer, that might be a quick operation. If you're on a quantum computer, maybe it's a super fast operation. If you're on a slow computer, then it could take a day. But yeah, so just something to think about there. Um,
Okay. Well, yeah, we're over time, so maybe that's a good spot to leave it for now. I do think this is one of those things that we're gonna have to keep coming back to with. I know, at least for myself, like it took a while for me to actually start writing concurrent code. So
Yeah.
maybe we come back to it at a later time if people have questions, right?
mhm.
But I think this is a good example of like how easy it is really to deal with
Yeah.
things that occur in, to make things atomic. This atomically function is like extremely powerful. Like if you learn anything from today, it would be to like play around with this atomically function and try to understand some use cases of it, because it's extremely powerful. The fact that you're able to just very simply lock instructions, or sorry, lock instructions to that tvar is very powerful when you're dealing with concurrent programs.
Right. And also
So
too, it's like, yeah, fork IO and like atomically, it's like it's almost, I think it's interesting because like I found the same thing. Like it took a while to like get how to do concurrent programming in Haskell. The funny part about it is it's so simple. Like it's like it's the idea of like parallel processing is like complex, um, but like anyone here, I guarantee, could take what we've learned today and write our
Yeah.
program that started today, where we had just print. You could so easily, like, I could copy paste this code and you could write it in, um, fork 10 threads and print, or like ultimately change out whatever, right? Like I could literally even generalize this as a function of like.
Yeah, maybe that's something that we should, if you're interested in this, and we're not gonna do it right now, but something that you could do is try to have each thread increment the tvar by 1, and just try to count up to like 1,000 using like 5 threads, and like maybe print out like which thread is currently doing the work, and that'll give you a really good solid understanding of how this works, right? So say you've got 10 threads, so do that fork IO 10 times and have each one of them just run the same operation of increment the tvar by 1, and then like see what happens. See like put a print like in each one, put atomically print thread 1, and then do the operation, and then close out of the atomically thread 2, print thread 2, do the increment, and just see what order it happens in. That'll be really useful. Because
That
you're
sounds
seeing
good.
here, like, it's completely different.
So just to give myself just a kind of like high level kind of recap, you can tell me if I'm completely off base here. If so, like if you've written a program or application where you can have multiple users coming in it whilst it's running, you might want to you essentially want to use that fork IO just so that they're using different threads, so they're not literally having to wait for someone else to finish using it.
Yep.
And then if, however, that within that process that they might want to touch some sort of shared resource, you would then use atomically to say, well, whilst you're touching it, no one else can come in halfway through and touch it at the same time.
Absolutely. That's
And that
exactly
just
it.
it keeps it it keeps all those things quite atomized, if that makes yeah.
Yep.
Okay.
Yeah, because
think I'm-
even too, like like when we break this down, right, like a transfer just breaks down into a debit
Yeah,
and
exactly.
credit.
And if I can, there's 2 operations. So what happens if you're halfway through the transfer and so you do the debit, right? And then, so this is actually a perfect example. So you do the debit, you've just taken away the money, but then say someone else someone else is going to do a debit as well. Like, I don't know, what's the example? Like, for the credit part. Like, say you're halfway through, say you credit first, let's just say. You're expecting to have money, but if someone else comes in and does the request, they can make the debit impossible. So okay, so say my bank, I'm supposed to be receiving money, or no, I'm the one
So
sending money. I'm the one sending money, and someone else is trying to take money from me, right? If I've not received the money yet, and someone else comes and tries to send that money to me, then I'm not going to have I'm getting dyslexic with this, but effectively, like, if you've got 2
so
things that are trying to happen at once, you may or may not have the money yet, or you may have said, I'm going to send this. The one thread thinks you do have the money, and then it charges you, and you don't actually have the money because it was just taken from the other
yeah, so
thread.
like for example here, if we take away these sleeps, right, we kind of added in these sleeps to like get like an idea of like program execution. But this program, as it stands, will work, right? This will never have an error because I start it with 1, I transfer to Kyle, then this is going to run next. Kyle transfers it back to me, and then I transfer it back to him. Of course, it's going to work. And you can see how if we continue to like send back and forth $1, and we assume that it goes, debit, credit, debit, credit, debit, credit, debit, credit, debit, credit, debit, credit, and we continue that into infinity, right? I could literally like do this infinite times, and we know just by like simple logic that this will never fail. That's true. But like, let's say, if we think of this as like a stack, right? If we break up a transfer into a debit and credit. So, this transfer is going to write to the stack, which is going to run these in order, or is going to run what it receives in order. This transfer is not going to be the only transfer writing to the stack. And so this might say, we might have 2 threads, right? Thread 1, thread 2, and both are writing the instructions to the stack. And so this results in chaos, because the result could be that we get either what we hope for is debit, credit, or I guess let me just do this: debit 1, debit 2, credit 1, credit 2. We hope for debit 1, credit 1, debit 2, credit 2. But the thing is that this could result in many other scenarios where we have instead debit 1, debit 2, credit 1, credit 2. Right? And so like there's what the point I'm going to make here is that like for 4 possible values, for 4 possible instructions, there are 4 times 3 times 2 times 1, 12, 24 possibilities of ordering here, right? And there's only one which makes sense. And we want to ensure that that's going to happen properly, that it's going to be the one correct case of 24 every single time.
Yeah, I've got an example too, but
that's what
that's valid.
That's what atomically guarantees. And so, in the case here, we know that's why we can guarantee. That's why I can look at this program and say I guarantee that this is going to succeed every single time, is because of the use of atomically.
Yeah. Yeah, I did a quick, just because I was trying to explain and I got dyslexic, so I put it on my my screen here. If you can take a look at my screen for a second. So let's say we have 2 threads. The first thread is I'm doing a transfer from my savings to my checkings, and then I want to spend the money, and that's all of the money in the checking. But then thread 2 is requesting money from my checking account. What the execution order that we would want would be like this: 1, then 2, and then 3, right? But without using atomic operations, we might get, just based on the timing of how long things take, we might get the red. So what might happen first is, okay, the money's transferred to Kyle from savings to checkings. But then this thread 2 runs and it says, hey, Kyle's got the money, let me take it. And then all of a sudden, this one fails. Right? Because thread 2 interacted with the memory that was inside of the checkings TVAR, or well, it wouldn't be a TVAR in this case, the checking account cache value. It's going to say, hey, he's got the money, I'm going to request that. Whereas what we would have expected is we would have expected a failure here. We want to have a failure here because he doesn't have his money, right? And so this depends on the application logic. You know, maybe this is like a more important transaction than this, right? But this is the idea that like we're forcing that this step happens before this one, and this thread must wait for this to be finished. Does that make sense? Cool. It was in my head and I needed to get it out on paper. But yeah, both what Galen and I are saying are correct. It's like this is like between threads. You want to ensure that you have that sequencing, and it's primarily to avoid race conditions where like this thing, because let's say transferring money took so long, this then happens before this one, and then that causes issues. So yeah.
Do you have any questions?
I think we're an hour over time, so we can probably end it here. Thanks to everyone who stayed late.
Mm-hmm.
Thank you. That's really, really interesting.
Worries. Yeah, make sure you put your email in the chat, and we'll send you the video recording. So yeah. Oh, oh. Okay, perfect. No, everyone's good.
You got it, yeah.
Okay, let me just.
Thanks, Gavin and everyone. I guess today is my first day. I guess today is the first day I'm joining the community. I was supposed to be here since last week, but unfortunately something took my time. And great
Yeah.
have everyone, and looks amazing.
We're happy.
Learned a lot.
Sorry, I keep interrupting you. We're happy to have you here this week. You know, so it's too bad for last week, but you're here this week. So
Yeah.
How'd you find the session for your first session?
Yeah, it was great. I get to learn a lot about Haskell. I think it's not a language that I have any experience in. So it's the first time that I'm actually taking a look at the syntax, and as I saw you writing it, kind of freaked me out a little, but it's amazing. I learned a lot. The theoretical part, I absolutely get it perfectly right, as I understood race conditions and the needs for atomically and all of that. I did learn a lot. Haskell seems to be.
I will say for your first time, if you've never seen Haskell before, Galen's kind of a whiz, and he just kind of writes the code really fast, and that's awesome, because eventually we're gonna have everyone else here is gonna be like that. But it really is. You'll start to understand it more, and I think this aspect of just like watching someone else write code in a language that you don't know is very helpful. But we do also have training materials for you to actually learn the language, so please check those out. They're on the ACE website. And if you have any questions about the language, ultimately you're gonna have to just start working with it, and then it'll start to make sense. You can think of it, it's the execution rather than like order of operations, like sequentially, like instructions. It's like one massive math expression. So like if you know what BEDMAS is, like brackets, exponents, division, multiplication, application, subtraction, it follows that same rule where like it's executing what's inside the brackets first, and then it builds out. So it's like one massive math expression is the easiest way to kind of think about how it executes. And then there's a lot of syntax like the $sign, which is basically just a parentheses. But you'll learn about all of that, and it'll start to make more sense once you see it. Yeah, but
Yeah.
like seeing it for the first time is scary. We'll just say that
Definitely.
because there's a lot of symbols, but those symbols are really just functions. And then once you learn what those functions do, you're like, oh, okay, that's very easy.
Yeah, the actual like true syntax of Haskell is very small. There's like I think 5 or 6 total keywords, and then like 3 different symbols that are actual true syntax, and everything else is just a function. And so as soon as you like kind of get like what is what is truly a function, then like it starts to become very approachable. So
Yeah. There's technically less syntax in Haskell than there is in Python.
Mm-hmm.
So it's but people look at Haskell and they're like, oh my gosh, what is this? So yeah, just give yourself some time, give yourself a pat on the back for being here, and we'll get you into using it.
Yeah.
Cool. Thanks for
Thanks,
joining.
Cal.
Thanks for coming on camera.
Everyone.
And also
Yeah.
too, like especially like this goes for everyone in the community, but like feel free to ask like a billion questions. Like if something's confusing, it's probably confusing for a lot of people. As we said, Haskell can be confusing to start with, and there's probably people who in the community who will like jump to help, but also of course we're here to help, and so like any question that you ever have, like there's no such thing as a stupid question. We're never going to be like you haven't read enough or some kind of crap, right? We're going to help you out. So we want to see like we are literally financially motivated to see you guys succeed. So like please help us help you kind of by like asking questions. So yeah.
Cool. All right. If no other questions, I think we can call it here. Nick, if you are having troubles with Nix, let me know because other people are probably going to have those same issues. Admittedly, I haven't. It's been a while since I've gotten what's it called? Persistent working with Obelisk. Usually Obelisk does it come bundled with Beam, Galen? Or is it's just kind of like Beam is kind of like what they use instead of Persistent typically?
Rhyolite. Well, it's actually technically like Rhyolite, which is like
Right.
easy to bundle with. Yeah, easy to bundle. Sorry.
But ultimately, like you're not going to be the only person to have this problem, so I can help you fix that. And then when you do, we probably want to document that in the lesson because if other people are using Persistent, they might run into the same issues.
Yeah, I've kind of still hit and I've tried a few different things, still running into the same issue. So yeah, happy to jump on and try and fix that if you want to. But I think in the meantime, just to get me back going on with actually doing some work, I've just decided to just use SQLite simple library, which at least lets me build a simple database and carry on working on the project. But yeah, if you want to put if you want to arrange some time there to sit there and try and problem solve it, let me know. I'm not fully on board to do that because I'll learn more about Nix, which I definitely need to learn more about as well.
Even too, like I mean, I'd have to limit it to like 10 minutes, but could quickly go through it now. I forget what time it is there, but I've been dealing with a lot of Nix lately. So there's just a trick to dealing with the packages I find. But yeah, I could maybe help with that.
Yeah, I can show you what's happening if that makes sense.
Sure.
Do you want to share my screen?
Sure.
Yeah, give her.
Okay. So let me know which one we'll go for. Screen 1, is that the right screen?
And everyone else, feel free to drop off, or you can stick around and see. You might learn something, but the session is technically over now. So.
Oops.
There's definitely some good things to learn.
Okay, I think that's the right screen. Yep. So if I'm in here, and let's say I go to backend and into the backend cabal. So I know I've got this quite simple there, but I'll just add in persistent. Oh, let me just show you that it's not complaining at this point. So I'll do ob run.
And by the way, for anyone who's watching, you don't you don't need to use persistent. You can just use any database, and you don't need to even. There's a way to go about it without using like Nix at all, but like this is definitely an option to consider.
So yeah, you can see it's working. But so yeah, I wanted to use persistent because I just used it in a previous project, so I was thought that'd be quite nice.
Yeah.
But if it's just not the best thing to use with Obelisk, then that's fine as well. Well, it's technically installing it twice there. Persist. Okay.
There are some weird things with Obelisk just because of was it they're using an old version of GHC, Galen? I think they're upgrading it though, right?
Yeah.
You were saying something about that.
You know, it's not even that old, but it's just like GHC has done so much lately that like it's
Yeah.
But
Like the difference between GHC 8 and 9 is like insane.
yeah, literally like the JavaScript backend being integrated into GHC is the core thing. But there's far more developments, but I'm not doing them justice. And I know Obelisk is also doing a huge change to make it simpler to. I think if I understand correctly, Kyle, I think they're getting rid of Reflex Platform and just like Haskell and Nix.
Thank God.
Really?
Like, well, getting rid of, are they integrating it into Obelisk?
Like, no, I think I think they're
Reflex Platform being on its own is annoying, but I love what it does.
what's annoying about it? I'm just curious. I've never like
Well,
it's hard to
I
read.
like having Obelisk, but
Uh-huh.
like Reflex Platform is kind of on its own. Like, and setting them up to work together is I found was like kind of a pain, but like if it's integrated into Obelisk, that would be,
Oh,
in my opinion, the best.
yeah. So sorry. I just
Yeah.
you want to do ob run dash v. It's real
Okay.
stupid. Like they really hide too much information, and then like what does that do there? These packages was not found. Okay, yeah. So you get the ASON error. So okay, this is saying that persistent is complaining about the ASON version. The first thing I would try is can you do jailbreak persistent? So open up default.nix. So implicitly, oh, okay. I gotta. I'm gonna share my screen as well here.
Yeah, go for it.
Cause I gotta remember how to even do this.
Yeah, the default.nix is a little different
Yeah.
from what.
Okay, there we go. Ace. Default.nix. How do I do this again? It is overrides. Okay, yeah. So you want to say overrides, or yeah. How do I do this? Project. I guess you could do. You don't have to do that necessarily. On line 2, add another attribute to the project. Or sorry, not line 2. I was the lines changed. I just didn't realize that.
Yeah.
So yeah, in that bracket for project, indent and start an override. Oh, sorry, go to the end of the line. I'm not explaining this well.
Okay.
And then tab, or like not tab, enter, press enter. Yeah. Okay, so overrides equal self colon super colon and then do the curly braces, and then start a new line. So now you want to say persistent equals and you need packages here to do this.
Yeah, I think you just add with packages, right?
Well, in project there, project in the curly braces. Yeah, add packages. And that's just because like we're not pattern matching on any of the arguments that the project function is giving us. That's the Reflex platform project function, by the way, or it effectively is, Kyle. But
Okay.
it's Obelisk project, which is just basically built directly on top of Reflex platform project.
Nice.
Yeah.
Yes, yeah. That's why I think they should just include it into the. Anyways, I digress.
Yeah, I guess like the point of like Reflex platform is to be able to like build your
It's
own
native stuff.
obelisk. Yeah, build your own obelisk. Like if you don't like the fact that it's like using obelisk routing or whatever. Okay, but so packages dot Haskell dot lib dot do jailbreak. I'm trying to remember. It is just as simple as super. Yeah. Okay. And then do jailbreak. Super dot persistent.
What dot?
Oh, sorry.
In parentheses.
Space.
Or space, yeah.
Oh, leave a space, then super.
Dot persistent.
What was the next bit? Dot persistent. Okay.
And then do jailbreak is a lowercase b.
Oh yeah.
Hmm.
Yeah.
And let's try to build. So yeah, this is just saying like get rid of the version bounds that persistent demands. And so it will either see that this succeeds or that the types don't work. Right, we'll try to build this and we'll say like could not match this type with this type.
No, it's doing more than it did last time.
Because before it was saying I refuse to even start building because I don't have the correct version bounds. Yeah, like I've noticed too. So I like when I submitted a package to the Hackage like repository or the like I added a package to the Hackage list, whatever you call it. They're very like intense about like what version bounds you have, and like they want it to be very specific. So they want it to be like this specifically works with ASIN version 2.0.1 and nothing else. Whereas like it actually might work with like 7 different versions of ASIN. So yeah.
Yeah, it's mostly because they want to like you can see all these deprecation warnings now, and that's kind of the trade-off. Like I believe, correct me if I'm wrong, Galen, when you do this without jailbreaking and you have the correct bounds, like you shouldn't get nearly as many deprecation warnings. But here, what we're doing is we're just forcing it to use a package that it might have some deprecated stuff, but it's still going to compile, right? Like we still know.
Actually, sorry, I'll say like the reason we're seeing the deprecation warnings here is just because we're building it. Normally, if you have like the typical persistent from just like the Nix cache, it's already pre-built, and you're just like
okay, that's fine. Yeah. So they might still have deprecation warnings in there.
Yeah, but like you're just you're not changing anything about persistent. You're just changing the dependencies of persistent.
Yeah.
All right. I think
it'll just find the one that works.
Yeah.
Oh,
What do we get here?
boom.
Boom.
It's running.
Let's go.
Fantastic.
There you go. 10 minutes.
As simple as that. Well done, Galen.
Hey, I've had some people tell me how to use it, so I don't even know the syntax properly. I'm like, you do this and then.
I think you can jailbreak that. Yeah. And that's again, that's like a growing pain of Nix in Haskell is like they kind of just have this like backdoor called jailbreaking
Yeah,
where it's like, okay, if it's not perfect, so if you can't get it to work, try jailbreaking.
totally. Like if I don't know, like this is our like Nix file here, like, and it's kind of cool. Like you can do a bunch with it. Like I have a lot of overrides, and you can see I have a lot of dead overrides. I'll just delete this. But like I was trying to build a like particular like markdown version with Obelisk, and like I needed particular versions, so like I was able to do like to pick some older versions. You can like there's this other function here like self.call hackage, where like you can very easily pick a version instead of the default version that this version of Nix packages would have, right? Like Nix packages is just kind of like it's almost like it's kind of meant to be like a beginner-friendly way to use Nix, right? And so it tries to like have a set of packages which will all build together, right? And like, but like ultimately, what you're probably using Nix for is like to pick particular versions of a package, and so yeah.
Yeah, just because the versions on Nix work doesn't mean that within that version the Haskell packages all work together,
Yeah.
right?
Yeah, exactly. And like,
Because Nix is not Haskell, right? Nix is like much bigger than Haskell, so that's why like Haskell is just one subset of the packages folder.
right.
Of the packages derivation,
Yeah.
is it?
Um,
Or no. The packages package, repository, whatever you call it.
yeah. Well, there literally is a Nix packages repo.
Yeah.
Yeah. So yeah, so like honestly, that's like the default thing I do. If I see like these version bounds don't work or whatever, I just do jailbreak of whatever package is depending on that package. Right, so it's persistent, not like the version of ASIN. So you jailbreak persistent, and then it works with that version of ASIN. So yeah, and you'll get that a lot because of Haskell decisions, like we spoke about. But that's yeah. I think that's definitely a lot of time on call today. So, but yeah, let us know. Like, and the same goes, for anyone else on this call. Like, at the end of a call, like, just let us know what kind of issues you're having. If it's something that you think like we could do quickly, like we're happy to help. So.
Brilliant. Thank you very much. I will get on with my project. Thank you.
Heck yeah.
Awesome.
Well, peace out, everyone, and I'll send you guys all the video and the recording.
All right.
See you in a bit.